Hi, my name is Chris Bennett. I'm an astrochemist from the Georgia Institute of Technology, and I'm going to be giving a critical eye from a scientist on the talk by Carl Palmer on amazing water. So first of all, I'd just like to say excellent talk, Carl, and you definitely covered like most of the important topics. So I think the best thing for me to do, rather than go through all of this again, is to maybe just put this in some context and suggest some of the other solvents that are being considered by astrobiologists, as well as how likely it might be for us to detect water in other environments, either in the solar system or outside of it. So first of all, I just want to provide the properties of some other solvents which are favored by astrobiologists. So I've listed the solvent here, polarity, chemical formula, melting point, boiling point, heat capacity, and dielectric constant. These are all things that Carl talked about previously. And I'm also just I've added a column here which I've just made up based on my own personal biases on the availability of these compounds in different environments. So if we go through water, you can see that's a polar molecule, the formula is H2O, it melts at 273 Kelvin, its boiling point is 373 Kelvin, so there's a range of 100 Kelvin there. It has a high heat capacity, a high dielectric constant, and it's a very available molecule, very abundant. Formamide, on the other hand, its properties, as you can see, is polar. Its chemical formula is a little bit more complicated. Its melting point is similar. Its boiling point is even higher than water. So there's almost another 100 Kelvin range there that it has. Its heat capacity is high. Its dielectric constant is very high. So this solvent could potentially be very, very good. My largest criticism of it is that its availability, particularly in a prebiotic context, is very, very low. It's a fairly complicated molecule. So it has two positives I would briefly mention though. The first is that its boiling point is higher than water, which means if you have an area which is too hot for water to exist, you might be able to get little pools of formamide, which are, where formamide will be the main solvent. And this is good because actually, particularly for a lot of prebiotic chemistry, because it actually turns out that a lot of reactions prebiotically are trying to get rid of water. So if your solvent is water, they turn out not to be very favorable, in which case formamide represents a very good alternative. But I think overall the availability being very low ruins that one for me. The other one is methane, and I just want to bring up why this is important. So Titan is a very large moon of Saturn, and we currently have a spacecraft called Cassini, which has been orbiting Saturn since 2004. And what this has done is it's actually been able to probe under these clouds and see lakes of liquid methane, but also two other related hydrocarbons, ethane and propane. And so these would have very similar properties to methane. So methane is at the other end of the scale. It's a nonpolar molecule. It's very simple, which means that it's going to be fairly common. And it has a high heat capacity. Its failing point is that it's firstly very, very cold, so it's only going to be liquid in the outer solar system at high pressure. And this range is about 20 Kelvin. This would be extended a little bit with the higher hydrocarbons. There'd be a little bit broader, a little bit more stable, higher temperatures. And it also has a very low dielectric constant, which means it's not going to be very easy for things like reactions involving ions and charged compounds. So the idea with the nonpolar and why a lot of astrobiologists like this one is because it's basically like a reverse world than Earth. So if you have, for example, a beaker and you add water and oil to it, the polar molecules like to be around other polar molecules. Same thing for the nonpolar molecules. What ends up happening is the hydrophobic molecules are repelled by the water and they end up forming two separate layers. Here, because you have the hydrocarbons are less dense than water, they will float to the surface on top. And this is a similar thing that Carl mentioned with the amino acids. So all of the enzymes in your body are made from peptides, which are made from amino acids. And these come in several different varieties, but some of them can be polar, which are attracted to water, and others are hydrophobic. And they're attracted to, sorry, I just realized that's wrong. Should be hydrophobic amino acids on the inside. So basically what happens is the ones that don't want to be around water will go up onto the inside of a molecule, and those that like to be on water will be on the outside. And this controls the peptide folding. So what you have for molecules is right on the inside, you have an active site where the actual chemical reaction occurs, and this can be completely controlled by the peptide folding process. And the idea is in Titan, you can actually have inverse proteins. So this would be the case, you have the hydrophobic compounds on the outside, which are surrounded by the solvent, and on the inside you can have the hydrophilic amino acids. So what you'll notice though is that obviously water is probably the best solvent, and this is why a lot of the goals of NASA and astrobiology have been follow the water. And what you'll see is a lot of missions tend to follow the same methodology. The rationale for this is, again, like we only have one example of life, which is Earth, and wherever there is life, wherever there is water, there is life. This includes, this is mostly due to this fairly recent development. We've discovered a lot of extremophiles that exist in places you wouldn't expect them to. And I'm going to give you just a few examples for some other places in the solar system that are of importance for missions and environments on Earth that are analogs to them. So, for example, there are some extremophiles called endoliths, and these organisms are found in rocks, and they've been found so far up to like 3-kilometer depths. That's not a restriction from the endoliths, that's a restriction by how far down we've drilled. So probably they're further down than that. And clearly these require very little water. The reason how they get around this problem is they actually have very slow metabolic rates. So they might only reproduce on timescales of like 10,000 years or something like this. And this is, of course, an analog for Mars. What we have here is the Curiosity rover. This is a little selfie that we took on the Mars surface. What we know about Mars is there was an ocean a long time ago, but now it's quite dry. So if there are any remnants for life, they would probably be these kind of endolithic extremophiles. Another example is Lake Vostok. So this is on Earth again. This is in Antarctica. There is a body of water some 2 miles under ice. And this has been isolated for millions and millions of years without receiving any sunlight. So the organisms, they've just recently pulled up cores, I think like last year or so, from down here, and they are teeming with life still. So these have been isolated without any light for about 2 million years and are still able to exist as organisms and reproduce. So there are several places in the solar system that are candidates for liquid water. The first of which is Europa. This is a moon of Jupiter, and this is an analog of, well, Lake Vostok is an analog for Europa, which is thought to contain a shell of around about 10 to 100 kilometers thick of ice. And there's a mission right now called Europa Clipper, which they're planning to send to Europa to try and get under this ice shell and see if you can sample if there's water underneath and maybe if there's potentially life. Another example is this moon called Enceladus, which recently got a lot of attention because the Cassini spacecraft, which I previously mentioned, managed to find these plumes of water emanating out here. And this, I believe, is the only detection of liquid water that's been found elsewhere in the solar system. Okay, so just also wanted to point out that water is extremely abundant. If you take a look at the abundances of the elements throughout the galaxy and interstellar medium, we just have some pretty pictures here of interstellar clouds, which are very pretty. And sorry, got lost sidetracked for a second. So if you look at these abundances, you can see that the most 2 abundant elements are hydrogen and oxygen. There's helium, but that's inert. So it makes sense that you'd think there's going to be quite a lot of water around when you consider all the other elements. And so water, you can actually detect these molecules in space, and you can tell that water is the most abundant solid compound in the interstellar medium. Interstellar just means between the stars, so the space between the stars. And in fact, the signal is so strong that we were able to see water from other galaxies. So this is an example of our closest one, the Andromeda Galaxy, which is 2.5 million light years away. The water story that I was telling you about is from a galaxy 7 billion light years away. So that's before our solar system even formed. Okay, so there's a lot of hope to try and find exoplanets that might be able to sustain life. And again, one of the key criteria for this is, at the moment, if they can hold liquid water. So this is a diagram showing Earth. At the top here, we have solar masses versus distance from the sun. So this is our solar system. We have Earth at 1 and 1. And then all of the other planets in our solar system. And you can see that Earth and Mars lie within this blue area, which is called the habitable zone, along with a few other stars that have been detected, well, exoplanets that have been detected that lie in this habitable region. And so what you'll notice, is that our current detection methods bias the results that we have higher mass exoplanets that are close to the star. These are just easier to detect. One of the reasons being that the shorter they are, they revolve around the sun a lot faster time periods, so they're much easier to detect. But it's possible that there are going to be more, as our telescopes get more and more advanced, we're going to find more Earth-sized planets out at larger distances from their stars. So just to notice this slope here is because as the stars are cooler, obviously, to get in that habitable zone, they need to be much closer to the star. And also, if you get any closer to the star than that, what ends up happening is you get the runaway greenhouse effect, which is where the water, basically the oceans, evaporate, and you end up, because they are greenhouse gases, with a runaway greenhouse effect. I'm not going to mention that too much because I believe that's being thought about by someone else here. Similarly, if you go on the other end, you end up freezing all the water, and what happens then is frozen water has a very high albedo, which means it has a high reflectivity, so all of the solar radiation just gets reflected off, and you end up cooling the planet even further. So there's feedbacks on this side and feedbacks on this side, both very bad. And so just like to say that water vapor so far has been detected in some Jupiter or Neptune-sized exoplanets, but nothing terrestrial so far. And the extrapolation given by a lot of exoplanet hunters is that perhaps as many as 1 in 2 to 10 stars could host a habitable planet. And what they mean by that is that it could have the right conditions for liquid water. Excuse me. So the last thing I'd like to just say is that liquid water does not mean life, which is a common misconception that people have. Just like to say that there are a lot of different factors, particularly for Earth, that have shaped the evolution. Some of these include the fact that we had, shortly after the formation of the solar system, an impact with a Mars-sized body that would have drastically changed the early evolution of the Earth. And also the Earth, something that has been mentioned is that we have a magnetic field and an thick atmosphere that shields the Earth from the atmosphere from the solar wind and solar radiation. And so people think this might be why Mars had lost its water, which is currently being investigated by the MAVEN spacecraft. So yeah, the timing and delivery of water to Earth is critical. As I mentioned, it disrupts a lot of prebiotic chemistry. So, for example, when you're trying to make peptide bonds to make peptides from amino acids, you're removing a water molecule, and this process cannot happen when you have a lot of water around. So yeah, it may be easy to find a lot of large ocean worlds, but it may be difficult for life to get started there. So yeah, that's pretty much what I had to say, is that our system was unique. Okay, all right, that's all I have to say. I'll try and get my email address to Carl. If anyone has any comments or concerns, you can email me and I'll try and answer those.